PIC is a family of modified Harvard architecture microcontrollers made by Microchip Technology, derived from the PIC 1650 originally developed by General Instrument's Microelectronics division. The name PIC initially referred to Peripheral Interface Controller, now it is PIC only. PICs are popular with both industrial developers and hobbyists alike due to their low cost, wide availability, large user base, extensive collection of application notes, availability of low-cost or free development tools, and serial programming capability. History. The original PIC was built to be used with General Instrument's new CP 1600 16-bit CPU. While generally a good CPU, the CP 1600 had poor I/O performance, and the 8-bit PIC was developed in 1975 to improve performance of the overall system by offloading I/O tasks from the CPU. The PIC used simple microcode stored in RAM to perform its tasks, and although the term was not used at the time, it shares some common features with RISC designs. In 1985, General Instrument spun off their Microelectronics division and the new ownership cancelled almost everything Euro, which by this time was mostly out of date. The PIC, however, was upgraded with an internal EPROM to produce a programmable channel controller. Today a huge variety of PICs are available with various onboard peripherals and program memory from 256 words to 64K words and more. PIC and PIC micro are registered trademarks of Microchip Technology. It is generally thought that PIC stands for Peripheral Interface Controller, although General Instrument's original acronym for the initial PIC 1640 and PIC 1650 devices was Programmable Interface Controller. The acronym was quickly replaced with Programmable Intelligent Computer. The Microchip 16C84, introduced in 1993, was the first Microchip CPU with on-chip EEPROM memory. This electrically erasable memory made it cost less than CPUs that required a quartz erase window for erasing EPROM. By 2013, Microchip was shipping over 1 billion PIC microcontrollers every year. Core architecture. The PIC architecture is characterized by its multiple attributes, separate code and data spaces. A small number of fixed-length instructions, most instructions are single-cycle execution, with one delay cycle on branches and skips, one accumulator, the use of which is implied. All RAM locations function as registers as both source and/or destination of math and other functions. A hardware stack for storing return addresses, a small amount of addressable data space, extended through banking, data space mapped CPU, port, and peripheral registers. ALU status flags are mapped into the data space. The program counter is also mapped into the data space and writable. There is no distinction between memory space and register space because the RAM serves the job of both memory and registers, and the RAM is usually just referred to as the register file or simply as the registers. Data space. PICs have a set of registers that function as general-purpose RAM. Special-purpose control registers for on-chip hardware resources are also mapped into the data space. The addressability of memory varies depending on device series, and all PIC devices have some banking mechanism to extend addressing to additional memory. Later series of devices feature move instructions which can cover the whole addressable space, independent of the selected bank. In earlier devices, any register move had to be achieved via the accumulator. To implement indirect addressing, a file select register, and indirect register are used. A register number is written to the FSR, after which reads from or writes to INDF will actually be to or from the register pointed to by FSR. Later devices extended this concept with post and pre-increment decrement for greater efficiency in accessing sequentially stored data. This also allows FSR to be treated almost like a stack pointer. External data memory is not directly addressable except in some high pin count PIC-18 devices. Code space. The code space is generally implemented as ROM, EPROM or flash ROM. In general, external code memory is not directly addressable due to the lack of an external memory interface. The exceptions are PIC-17 and select high pin count PIC-18 devices. word size, all PICs handle data in 8-bit chunks. However, the unit of addressability of the code space is not generally the same as the data space. For example, PICs in the baseline and mid-range families have program memory addressable in the same word size as the instruction width, that is 12 or 14 bits respectively. In contrast, in the PIC18 series, the program memory is addressed in 8-bit increments, which differs from the instruction width of 16 bits. In order to be clear, the program memory capacity is usually stated in number of instructions, rather than in bytes. Stacks. PICs have a hardware call stack, which is used to save return addresses. The hardware stack is not software accessible on earlier devices, but this changed with the 18 series devices. Hardware support for a general-purpose parameter stack was lacking in early series, but this greatly improved in the 18 series, making the 18 series architecture more friendly to high-level language compilers. Instruction set. PIC's instructions vary from about 35 instructions for the low-end PICs to over 80 instructions for the high-end PICs. The instruction set includes instructions to perform a variety of operations on registers directly, the accumulator and a literal constant or the accumulator and a register, as well as for conditional execution, and program branching. Some operations, such as bit setting and testing, can be performed on any numbered register, but operand arithmetic operations always involve W, writing the result back to either W or the other operand register. To load a constant, it is necessary to load it into W before it can be moved into another register. On the older cores, all register moves needed to pass through W, but this changed on the high-end cores. PIC cores have skip instructions which are used for conditional execution and branching. The skip instructions are skip if bit set and skip if bit not set. Because cores before PIC18 had only unconditional branch instructions, conditional jumps are implemented by a conditional skip followed by an unconditional branch. Skips are also of utility for conditional execution of any immediate single following instruction. It is possible to skip instructions. For example, the instruction sequence skip if A. Skip if B. C will execute C if A is true or if B is false. The 18 series implemented shadow registers which save several important registers during an interrupt, providing hardware support for automatically saving processor state when servicing interrupts. In general, PIC instructions fall into 5 classes: operation on working register with 8-bit immediate operand. For example, MOVLW, ANDLW. One instruction peculiar to the PIC is RETLW, load immediate into WREG and return, which is used with computed branches to produce lookup tables. Operation with WREG and indexed register. The result can be written to either the working register or the selected register. Bit operations. These take a register number and a bit number, and perform one of 4 actions: set or clear a bit, and test and skip on set clear. The latter are used to perform conditional branches. The usual ALU status flags are available in a numbered register, so operations such as branch on carry clear are possible. Control transfers. Other than the skip instructions previously mentioned, there are only 2, goto and call. A few miscellaneous zero-operand instructions, such as return from subroutine, and sleep to enter low-power mode. Performance. The architectural decisions are directed at the maximization of speed-to-cost ratio. The PIC architecture was among the first scalar CPU designs, and is still among the simplest and cheapest. The Harvard architecture in which instructions and data come from separate sources simplifies timing and microcircuit design greatly, and this benefits clock speed, price, and power consumption. The PIC instruction set is suited to implementation of fast lookup tables in the program space. Such lookups take 1 instruction and 2 instruction cycles. Many functions can be modeled in this way. Optimization is facilitated by the relatively large program space of the PIC and by the design of the instruction set, which allows for embedded constants. For example, A branch instruction's target may be indexed by W, and executor ETLW, which does as it is named, return with literal in W. Interrupt latency is constant at 3 instruction cycles. External interrupts have to be synchronized with a 4-clock instruction cycle, otherwise there can be a 1 instruction cycle jitter. Internal interrupts are already synchronized. The constant interrupt latency allows PICs to achieve interrupt-driven low jitter timing sequences. An example of this is a video sync pulse generator. This is no longer true in the newest PIC models, because they have a synchronous interrupt latency of 3 or 4 cycles. Advantages: small instruction set to learn, RISC architecture, built-in oscillator with selectable speeds, easy entry level, in-circuit programming plus in-circuit debugging PIC units available for less than $50, inexpensive microcontrollers, wide range of interfaces including EO2C, SPI, USB, USART, AD, programmable comparators, PWM, LIN, CAN, PSP, and Ethernet. Availability of processors and DIL package make them easy to handle for hobby use. Limitations: 1 accumulator, register bank switching is required to access the entire RAM of many devices. Operations and registers are not orthogonal. Some instructions can address RAM and/or immediate constants, while others can use the accumulator only. The following stack limitations have been addressed in the PIC-18 series, but still apply to earlier cores. The hardware call stack is not addressable, so preemptive task switching cannot be implemented. Software-implemented stacks are not efficient, so it is difficult to generate re-entrant code and support local variables. With paged program memory, there are 2 page sizes to worry about, one for call and GOTO and another for computed GOTO. For example, on PIC-16, call and GOTO have 11 bits of addressing, so the page size is 2048 instruction words. For computed GOTOs, where you add to PCL, the page size is 256 instruction words. In both cases, the upper address bits are provided by the PCL-ATH register. This register must be changed every time control transfers between pages. PCL-ATH must also be preserved by any interrupt handler. Compiler development: while several commercial compilers are available, in 2008, Microchip released their own C compilers, C18 and C30, for the line of 18F, 24F and 3033F processors. As of 2013, Microchip offers their XC series of compilers. For use with MPLABX, Microchip will eventually phase out its older compilers such as C18, and recommends using their XC series compilers for new designs. The easy-to-learn RISC instruction set of the PIC assembly language code can make the overall flow difficult to comprehend. Judicious use of simple macros can increase the readability of PIC assembly language. For example, the original Parallax PIC assembler has macros which hide W and make the PIC look like a 2-address machine. It has macro instructions like mov B, A, and add B, A. It also hides the skip instructions by providing 3 operand branch macro instructions such as CJNE, B, dist. Family core architectural differences: PIC microchips have a Harvard architecture, and instruction words are unusual sizes. Originally, 12-bit instructions included 5 address bits to specify the memory operand, and 9-bit branch destinations. Later revisions added opcode bits, allowing additional address bits. Baseline core devices: these devices feature a 12-bit wide code memory, a 32-byte register file, and a tiny 2-level deep call stack. They are represented by the PIC-10 series, as well as by some PIC-12 and PIC-16 devices. Baseline devices are available in 6-pin to 40-pin packages. Generally the first 7 to 9 bytes of the register file are special-purpose registers, and the remaining bytes are general-purpose RAM. Pointers are implemented using a register pair. After writing an address to the FSR, the INDF register becomes an alias for the addressed register. If banked RAM is implemented, the bank number is selected by the high 3 bits of the FSR. This affects register numbers 16 a Euro 31. Registers 0 a Euro 15 are global and not affected by the bank select bits. Because of the very limited register space, 4 rarely read registers were not assigned addresses, but written by special instructions. The RAM address space is 512 words, which may be extended to 2048 words by banking. Call and GOTO instructions specify the low 9 bits of the new code location. Additional high-order bits are taken from the status register. Note that a call instruction only includes 8 bits of address, and may only specify addresses in the first half of each 512-word page. Lookup tables are implemented using a computed GOTO into a table of RETLW instructions. The instruction set is as follows. Register numbers are referred to as F, while constants are referred to as K. Bit numbers are selected by B. The D bit selects the destination, 0 indicates W, while 1 indicates that the result is written back to source register F. The C and Z status flags may be set based on the result. Otherwise they are unmodified. Add and subtract instructions that set C also set the DC flag, the carry from bit 3 to bit 4, which is useful for BCD arithmetic. Ilan Microelectronics clones. Ilan Microelectronics Corporation make a series of PIC micro-like microcontrollers with a 13-bit instruction word. The instructions are mostly compatible with the mid-range 14-bit instruction set, but limited to a 6-bit register address and a 10-bit program space. The 10-bit program counter is accessible as R2. Reads access only the low bits, and writes clear the high bits. An exception is the TBL instruction, which modifies the low byte while preserving bits 8 and 9. The 7 accumulator immediate instructions are renumbered relative to the 14-bit PIC micro, to fit into 3 opcode bits rather than 4, but they are all there, as well as an additional software interrupt instruction. There are a few additional miscellaneous instructions, and there are some changes to the terminology, but the equivalents are obvious. Same opcode as 12-bit PIC. A Euro instruction unique to M78 instruction set with no PIC equivalent. Some models support multiple RAM or RAM banks, in a manner similar to other PIC microcontrollers. Mid-range core devices. These devices feature a 14-bit wide code memory, and an improved 8-level deep call stack. The instruction set differs very little from the baseline devices, but the 2 additional opcode bits allow 128 registers and 2048 words of code to be directly addressed. There are a few additional miscellaneous instructions, and 2 additional 8-bit literal instructions, add and subtract. The mid-range core is available in the majority of devices labeled PIC12 and PIC16. The first 32 bytes of the register space are allocated to special-purpose registers. The remaining 96 bytes are used for general-purpose RAM. If banked RAM is used, the high 16 registers are global, as are a few of the most important special-purpose registers, including the status register which holds the RAM bank select bits. The PCL-ATH register supplies high-order instruction address bits when the 8-bit supplied by a write to the PCL register, or the 11-bit supplied by a GOTO or call instruction, is not sufficient to address the available RAM space. Enhanced mid-range core devices. Enhanced mid-range core devices introduce a deeper hardware stack, additional reset methods, 14 additional instructions and a Eurocar Euro1 registered trademark programming language optimizations. In particular, there are 2 INDF registers, and 2 corresponding FSR register pairs. Special instructions use FSRN registers like address registers, with a variety of addressing modes. PIC-17 high-end core devices. The 17 series never became popular and has been superseded by the PIC-18 architecture. It is not recommended for new designs, and availability may be limited. Improvements over earlier cores are 16-bit wide opcodes, and a 16-level deep call stack. PIC-17 devices were produced in packages from 40 to 68 pins. The 17 series introduced a number of important new features: a memory-mapped accumulator, read access to code memory, direct register-to-register moves, an external program memory interface to expand the code space, an 8-bit hardware multiplier, a second indirect register pair, auto-increment decrement addressing controlled by control bits in a status register, PIC18 high-end core devices. Microchip introduced the PIC18 architecture in 2000. 2. Unlike the 17 series, it has proven to be very popular, with a large number of device variants presently in manufacture. In contrast to earlier devices, which were more often than not programmed in assembly, C has become the predominant development language. The 18 series inherits most of the features and instructions of the 17 series, while adding a number of important new features. Call stack is 21 bits wide and much deeper. The call stack may be read and written, conditional branch instructions, indexed addressing mode, extending the FSO registers to 12 bits, allowing them to linearly address the entire data address space, the addition of another FSO register, the RAM space is 12 bits, addressed using a 4-bit bank select register and an 8-bit offset in each instruction. An additional access bit in each instruction selects between bank 0 and the bank selected by the BSR. A one-level stack is also available for the status, WREG and BSR registers. They are saved on every interrupt, and may be restored on return. If interrupts are disabled, they may also be used on subroutine call return by setting the S-bit. The auto-increment decrement feature was improved by removing the control bits and adding 4 new indirect registers per FSR. Depending on which indirect file register is being accessed, it is possible to PIC decrement, post-increment, or pre-increment FSR. Or form the effective address by adding W to FSR. In more advanced PIC18 devices, an extended mode is available which makes the addressing even more favorable to compiled code, a new offset addressing mode. Some addresses which were relative to the access bank are now interpreted relative to the FSR2 register, the addition of several new instructions, notable for manipulating the FSR registers. These changes were primarily aimed at improving the efficiency of a data stack implementation. If FSR2 is used either as the stack pointer or frame pointer, stack items may be easily indexed allowing more efficient reentrant code. Microchip's MPL-ABC18C compiler chooses to use FSR2 as a frame pointer. PIC24 and DSPIC 16-bit microcontrollers. In 2001, Microchip introduced the DSPIC series of chips, which entered mass production in late 2004. They are Microchip's first inherently 16-bit microcontrollers. PIC24 devices are designed as general-purpose microcontrollers. DSPIC devices include digital signal processing capabilities in addition. Although still similar to earlier PIC architectures, there are significant enhancements. All registers are 16 bits wide, data address space expanded to 64 kbytes, first 2K is reserved for peripheral control registers, data bank switching is not required unless RAM exceeds 62K, F-operand direct addressing extended to 13 bits, 16W registers available for register-register operations. But operations on F-operands always reference WO. Program counter is 22 bits, instructions are 24 bits wide, instructions come in byte and word forms, stack is in RAM. There is no hardware stack, W14 is the frame pointer, data stored in ROM may be accessed directly, interrupt vectors for different interrupt sources are supported. Some features are, hardware MAC, barrel shifting, bit reversal, 16A, 16-bit single-cycle multiplication and other DSP operations, hardware divide assist, hardware support for loop indexing, direct memory access. DSPICs can be programmed in C using Microchip's XC16 compiler, which is a variant of GCC. Instruction ROM is 24 bits wide. Software can access ROM and 16-bit words, where even words hold the least significant 16 bits of each instruction, and odd words hold the most significant 8 bits. The high half of odd words reads as 0. The program counter is 23 bits wide, but the least significant bit is always 0, so there are 22 modifiable bits. Instructions come in 2 main varieties. One is like the classic PIC instructions, with an operation between WO and a value in a specified F register, and a destination select bit selecting which is updated with the result. The W registers are memory mapped. So the F operand may be any W register. The other form, new to the PIC24, specifies 3 W register operands, 2 of which allow a 3-bit addressing mode specification. The register offset addressing mode is only available to 2 operand instructions. 3 operand instructions use WW as the second source operand, and use this encoding for an unsigned 5-bit immediate source. Note that the same WW may be added to both WD and WS. A few instructions are 2 words long. The second word is ENOP, which includes up to 16 bits of additional immediate operand. PIC 32-32-bit microcontrollers. In November 2007, Microchip introduced the new PIC 32MX family of 32-bit microcontrollers. The initial device lineup is based on the industry standard MIPS 32M 4K core. The device can be programmed using the Microchip MPLABC compiler for PIC 32MCUs, a variant of the GCC compiler. The first 18 models currently in production are pin-to-pin compatible and share the same peripheral set with the PIC24FXX-GAOXX family of devices, allowing the use of common libraries, software and hardware tools. Today, starting at 28-pin in small QFN packages up to high-performance devices with Ethernet, CAN and USB OTG, full family range of mid-range 32-bit microcontrollers are available. The PIC32 architecture brings a number of new features to Microchip portfolio, including the highest execution speed 80 MIPS, the largest flash memory, 512 KB, 1 instruction per clock cycle execution, the first cache processor, allows execution from RAM, full-speed host dual-role and OTG USB capabilities, full JTAG and 2-wire programming and debugging, real-time trace. An upcoming product from Microchip is the PIC32MZ family of microcontrollers. Device variants and hardware features. PIC devices generally feature sleep mode, watchdog timer, various crystal or IC oscillator configurations, or an external clock. Variants. Within a series, there are still many device variants depending on what hardware resources the chip features. General-purpose I/O pins. Internal clock oscillators. 832-bit timers. Internal EEPROM memory. Synchronous asynchronous serial interface USART, MSSP peripheral for ES2C and SPI communications. Capture compare and PWM modules. Analog to digital converters. USB, Ethernet, CAN interfacing support. External memory interface. Integrated analog RF front ends. Keylogg rolling code encryption peripheral, and many more. Trends. The first generation of PICs with EPROM storage are almost completely replaced by chips with flash memory. Likewise, the original 12-bit instruction set of the PIC 1650 and its direct descendants has been superseded by 14-bit and 16-bit instruction sets. Microchip still sells OTP and windowed versions of some of its EPROM-based PICs for legacy support or volume orders. The Microchip website lists PICs that are not electrically erasable as OTP. UV erasable windowed versions of these chips can be ordered. Part number suffixes. The F in a name generally indicates the PIC micro uses flash memory and can be erased electronically. Conversely, a C generally means it can only be erased by exposing the die to ultraviolet light. An exception to this rule is the PIC 16C84, which uses EEPROM and is therefore electrically erasable. An L in the name indicates the part will run at a lower voltage, often with frequency limits imposed. Parts designed specifically for low voltage operation, within a strict range of 3 to 3.6 volts, are marked with a J in the part number. These parts are also uniquely I/O tolerant as they will accept up to 5 of E as inputs. PIC clones. Third-party manufacturers make compatible products, for example the Parallax SX. Development tools. Microchip provides a freeware IDE package called MPLAB, which includes an assembler, linker, software simulator, and debugger. They also sell C compilers for the PIC18 and DS-PIC, which integrate cleanly with MPLAB. Free student versions of the C compilers are also available with all features. But for the free versions, optimizations will be disabled after 60 days. Several third parties make C language compilers for PICs, many of which integrate to MPLAB and/or feature their own IDE. A fully featured compiler for the PIC BASIC language to program PIC microcontrollers is available from Me Labs, Incorporated. Microelectronica offers PIC compilers in C, BASIC and Pascal programming languages. A graphical programming language, Flowcode, exists capable of programming 8 and 16-bit PIC devices and generating PIC-compatible C code. It exists in numerous versions from a free demonstration to a more complete professional edition. The only open-source compiler for the PIC16 and PIC18 family is the SDCC. It makes use of Putils for linker and assembler tools. A plugin is needed to install them in MPLAB or MPLABX. Development tools are available for the PIC family under the GPL or other free software or open-source licenses. Device programmers. Devices called programmers are traditionally used to get program code into the target PIC. Most PICs that Microchip currently sell feature ICSP and/or LVP capabilities, allowing the PIC to be programmed while it is sitting in the target circuit. ICSP programming is performed using 2 pins, clock and data, while a high voltage is present on the VPP-MCLR pin. Low voltage programming dispenses with the high voltage, but reserves exclusive use of an I/O pin and can therefore be disabled to recover the pin for other uses. There are many programmers for PIC microcontrollers, ranging from the extremely simple designs which rely on ICSP to allow direct download of code from a host computer, to intelligent programmers that can verify the device at several supply voltages. Many of these complex programmers use a pre-programmed PIC themselves to send the programming commands to the PIC that is to be programmed. The intelligent type of programmer is needed to program earlier PIC models which do not support in-circuit programming. Many of the higher-end flash-based PICs can also self-program. Demo boards are available with a small bootloader factory-programmed that can be used to load user programs over an interface such as RS-232 or USB, thus obviating the need for a programmer device. Alternatively, there is bootloader firmware available that the user can load onto the PIC using ICSP. The advantages of a bootloader over ICSP is the far superior programming speeds, immediate program execution following programming, and the ability to both debug and program using the same cable. Programmers' debuggers are available directly from Microchip. Third-party programmers range from plans to build your own, to self-assembly kits and fully tested ready-to-go units. Some are simple designs which require a PC to do the low-level programming signaling, while others have the programming logic built into them. The following are the official Pic programmer debuggers from Microchip. Pic32 clones and open source. Pic32 has been an interesting PIC programmer for Microchip. It can program most PICs and debug most of the PICs. Ever since its first releases, all software source code and hardware schematic are open to the public. This makes it relatively easy for an end user to modify the programmer for use within non-Windows operating systems such as Linux or Mac OS. In the meantime, it also creates lots of DIY interest and clones. This open-source structure brings many features to the Pic32 community such as Programmer to Go, the UART tool and the Logic tool, which have been contributed by Pic32 users. Users have also added such features to the Pic32 as 4 MB Programmer to Go capability, USB buck boost circuits, RJ12 type connectors and others. Debugging, software emulation. Commercial and free emulators exist for the PIC family processors. In circuit debugging, later model PICs feature an ICD interface, built into the CPU core. ICD debuggers can communicate with this interface using 3 lines. This cheap and simple debugging system comes at a price, however, namely limited breakpoint count, loss of some I/O and loss of some features of the chip. For small PICs, where the loss of I/O caused by this method would be unacceptable, special headers are made which are fitted with PICs that have extra pins specifically for debugging. In Circuit Emulators, Microchip offers 3 full-in circuit emulators, the MPLA-BICE 2000, the newer MPLA-BICE 4000, and most recently, the Real ICE. All of these ICE tools can be used with the MPLA-BIDE for full source level debugging of code running on the target. The ICE 2000 requires emulator modules, and the test hardware must provide a socket which can take either an emulator module or a production device. The Real ICE connects directly to production devices which support in-circuit emulation through the PGC-PGD programming interface, or through a high-speed connection which uses 2 more pins. According to Microchip, it supports most flash-based PIC, PIC24, and DSPIC processors. The ICE 4000 is no longer directly advertised on Microchip's website, and the purchasing page states that it is not recommended for new designs. Operating Systems, an open-source project by Serge Vaklenko, adapts 2 Bahamian dollars and 11 cents to the Pic32 architecture, under the name RetroBSD. This brings a familiar Unix-like operating system, including an onboard development environment, to the microcontroller, within the constraints of onboard hardware. See also, PIC16x84, Atmel AVR, Arduino, Basic Atom, Basic Stamp, OAPIC, PICs, TMSP430, Maximit, References. External links, PIC microcontroller at DMOZ. Official Microchip website, PIC Wi-Fi projects website.